So this is problem number 3 from the 2015 AP Calculus AV exam. So I'll pause for a moment and give you a chance to read the problem. All right. So in this problem, you've got these two people that are jogging, right? So we're going to talk about Johanna first because she's mentioned in the problem. It says that her velocity from time 0 to 40 is given by a differentiable function v and selected values of v, which are in the chart above. So several pieces of information here. V is differentiable, so the derivative exists everywhere. The values for v are given here. This is the only representation we have of Johanna's velocity. And our units are in meters per minute for velocity and minutes for time. All those things could be important later in the problem. So part A says, use the data in the table to estimate the value of v prime of 16. So if I'm estimating a derivative, that's like estimating an IROC. So if I'm estimating an IROC and I don't have like an equation, the next best thing I can do is find an AROC around that value. So if you look in the chart, v prime of 16, 16 is in between 20 and 30. So if I'm trying to estimate v prime of 16, then I'm going to do that by doing the next best thing I can, which is finding an AROC between points nearby. So that would be the change in velocity. Oop, that's not 16, that's 12. Over the change in time. So v of 20, according to the chart, is 240, and v of 12, according to the chart, is 200. So I get 40 over 8, which is 5. Now, keep in mind what the meaning of that is. I've just taken an AROC. On top, it was meters per minute, and on the bottom, it was minutes. So this is meters per minute squared, so it represents acceleration at time 16. Now the question isn't asking units, but it's useful to know what the units mean. All right, so part B. It says, using correct units, explain the meaning of the definite interval from 0 to 40 of the absolute value of velocity in context of this problem. So keep in mind that the absolute value of velocity is the same thing as speed. And that takes a velocity from being a vector to being a scalar. So when I'm taking the antiderivative of a velocity or speed, that gives me a distance. And the scalar version of distance that we talked about was total distance traveled. So when I'm talking about a definite integral from 0 to 40 of an absolute value of velocity, what that means is this. It's the total distance traveled and the units, remember to ask for units, and that would be in meters for time 0 minutes to time 40 minutes. So the units on both what the integral means, the meaning, which is total distance traveled, and the units on the endpoints are all important to interpreting this. And then the rest of the question says, approximate the value of this integral using a right Riemann sum with the 4 subintervals indicated in the table. So the subintervals that we have, the 4 subintervals go from 0 to 12, so this one, from 12 to 20, this one, from 20 to 24, this one, and from 24 to 40, this one. And they said use a right Riemann sum, right? So we're going to be using the right-hand endpoints of these. So if we look at the first one, so let's say this integral is approximately. So the width of that first interval would be 12. And the height of that interval would be the right-hand endpoint's height, which would be 200. You go to the next interval, that width would be between 12 and 20, which is 8. And you use the height at 20, which is 240. Then you go to the third interval. The width of that interval would be 4. And be careful, the height of this interval, they said you wanted the integral of the absolute value of the velocity, not the velocity itself. So instead of using negative 220, which means we're moving 220 in a negative direction, you're actually going to use positive 220 because you're using the absolute values of the velocities. And then that last interval, the width is 16, and the height is 150. So this is a non-calculator part, unfortunately. So I'm going to have to do this arithmetic by hand. So this is 2400. 8 times 240 would be 3 times 64, which is 192. So this is 1,920. 4 times 220 is 880. And then 16 times 150, 15 times 15 is 225. Add a 15 is 240, and the 0 is 2,400. Obviously, you can do the multiplication out on paper if you'd like. So 2,400 per 400 is 4,800. That would be 5680, 6680, 7580. Looks like 7,600 meters. And again, I would go ahead and put the units on there, but they didn't ask for it in this part, so you can get away without it. So that's part B. No. Part C deals with a new person, deals with Bob. And Bob's riding his bicycle along the same path. For time 0 to 10, his velocity is modeled not by the chart above, but by this equation. So whenever we're referring to Bob, this is going to be his velocity. So t is measured in minutes, and t is measured in meters per minute. You want Bob's acceleration at time 5. Well, to go from velocity to acceleration, you take the derivative. And we want Bob's acceleration at time 5. So what we want to find is b prime of 5. In order to do that, we need to know b prime of t first. And b prime of t here would be 3t squared minus 12t, and the 300 goes away. And this implies that when I take 5 and plug it in, I would get 3 times 25, which is 75, minus 12 times 5, which is 60, and so that would be 15. And it didn't ask for units, but I would go ahead and put them anyway. That's meters per minute squared. And again, that's because we took the derivative of velocity. So that's the answer to part C. And then part D says, based on the model B in part C, find Bob's average velocity from the time 0 to the time 10. So keep in mind that when you're dealing with averages, if you're doing an average rate of change, it's an AROC. If you're doing average of a function that you have, it's average value of a function. So on this, part D, I want average velocity, and I was given velocity. So I'm going to use the average value of a function, which involves the integral. So Bob's average velocity would be, since we're going from 0 to 10, that's 1 over b minus a, which would be 10 minus 0, times the integral from 0 to 10 of the thing we're taking the average of, which in this case is his velocity with respect to time. So Bob's velocity, again, was t cubed minus 6t squared plus 300. So I would need to take 1/10 of the antiderivative of b of t. So let's see, that would be 1/4 t to the 4th minus 2t cubed plus 300t evaluated from 0 to 10. So this would be 1/10 of, so let's see, 10 to the 4th is 1,000, a 4th of that is 250. Nope, 10 to the 4th is 10,000, so let me add an extra 0 to that. 10 to the 3rd is 1,000, minus times 2 is 2,000. And then 300 times 10 is 3,000. And then when I plug in 0, there's t's in every term, so that whole thing would be just 0 as possible. So this would be 1/10 of 3,500, which is 350. And the units of that, since we're doing average velocity, will be 350 meters per minute. And that's part 3.